In this question, a scientist wants to determine the equilibrium constant, K, for the following fictional reaction at 434 Kelvin. Here's our fictional reaction. 2A plus 2M in our reactants and A2M2 in our products. We're also given two reactions down here, reaction 1 and reaction 2, and we're given the equilibrium constant for those reactions. Our goal is going to be combining those reactions from the table so that when we add them up, we get our goal reaction, and using the equilibrium constants of those step reactions to figure out what the overall equilibrium constant of our goal reaction is. The first part of this problem is very similar to the Hess's law problems from the thermodynamics unit. To start with, let's identify the reactants and products in our goal reaction. So in our goal reaction, we have A and M. Those are our reactants. So our reactants are A and M. For our products, we have A2M2. First, we're going to figure out for each of our reaction steps shown in the table, do we want to have them in the forwards or the backwards reaction? To do that, we're going to identify if our goal reactants and products are in their reactants or products, because we want the reactants in our goal equation to also be in the reactants of our steps, and the same for the products. We want the products of our goal equation to also be in the products of our steps. So let's look at reaction 1 first. In here, of the stuff in our goal equation, we've got A and M. So those are reactants in our goal equation. However, in this step 1 reaction, they are products. So we're going to want this equation to be backwards so that we get A and M in the reactants. So we're going to choose backwards direction is required. And I'm going to write out what that equation will look like when it's backwards. It's going to look like A gas plus M aqueous goes to AM liquid. Now we can see our reactants from our goal reaction are now in the reactants of this step. Now let's look at reaction 2. So of the stuff that's in reaction 2, A2M2 is the thing that appears in our goal equation. And in our goal equation, that's in the products. However, in this step, it's in the reactants. So again, we're going to want this equation to be backwards so that we can have A2M2 in the products in this step. So this one's also going to be backwards. And now we'll write down what that equation will look like when it's backwards. We'll start with 2AM, which is a liquid, and we'll end up with A2M2, which is a gas. Awesome, so we've got our directions chosen. Next, we have to figure out how many moles of each of those steps do we need so that those steps will add up to give this overall reaction. Let's start with reaction step 1. So we have A and M in this reaction. In our goal reaction, we have 2A and 2M. So that's telling us we're going to need 2 lots of this reaction here in order to get the right numbers of A and M in our goal equation. For reaction 2, we have A2M2, and in our goal equation, we just have A2M2, just one in each. So we already have the right number of moles of A2M2, which means we already have the right number of moles of reaction 2. So we just need 1 mole of reaction 2. So that's just going to multiply by 1. Okay, so we figured out the moles and direction required. Let's just test that out by adding up our equations together to check that we get the goal reaction. So we said we have 2 sets of our top reaction. So we've got 2A gas plus 2M aqueous, and that gives 2AM liquid. Then we've got 1 set of our step 2 reaction, and I'm going to add that on each side. So in our reactants, we've got 2AM, which is a liquid, and in our products, we've got A2M2, which is a gas. So there we've added together 2 moles of reaction 1 backwards and 1 mole of reaction 2 backwards. Now I can see if there's anything that can cancel out. I can see I've got 2Am on both the reactants and the product, so that's going to cancel out. And I'm left with 2A, which is a gas, plus 2M, which is aqueous, gives A2M2, which is a gas. And that matches up perfectly with our goal equation up here. So we've successfully found our goal equation. So that's just a little check we can do to make sure that we got the right number of moles and the right directions for each of those steps. Next, we need to calculate the equilibrium constant K for this reaction at 434 Kelvin. So we know we've got 2 moles of reaction 1 backwards, and we know the equilibrium constant of reaction 1 is 4,420. We also know we need 1 mole of reaction 2 backwards, and reaction 2 has an equilibrium constant of 4,810. So now we need to combine those equilibrium constants together to get our overall equilibrium constant for the goal reaction. So the way we're going to do that is to have a fraction. Now, if we have a reaction forwards, then the equilibrium constant for that reaction is going to go in the top of our fraction. If we have a reaction backwards, the equilibrium constant for that is going to go in the bottom of our fraction. In this question, both of our reactions steps are having backwards. So both of our equilibrium constants are going to go in the bottom of our fraction. So we're going to have 4420, because that's the equilibrium constant for step 1, multiplied by 4810, because that's the equilibrium constant for step 2. However, we also need to include the number of moles of each. And the way we include that is that it's to the power of. So for step 1, 4420 was the equilibrium constant. And we've got 2 moles of that. So it's going to be 4420 squared. For 4810 for reaction 2, we only needed 1 mole of that. So that's going to be to the power of 1. But remember, to the power of 1 is the same as the thing itself. So we don't need to include to the power of 1. And then the top of our fraction is just going to be 1 because we don't have any reactions going forwards. So we don't have any equilibrium constants up there. Awesome. So now we just put this into our calculator. That's going to get us a value of 1.06 times 10 to the power of negative 11. So we can go ahead and enter that in our answer box. Remember that on this platform, for times 10 to the power of, we just type in E. So this is going to be 1.06 E negative 11. Awesome. So we figured out our equilibrium constant. Finally, we're asked, are the products or reactants favored at equilibrium? Since our number is to the power of negative 11, that means it's a very small number. That's telling us our reactants are favored at equilibrium, because that number is way less than 1. If the number was way bigger than 1, that's telling us our products are favored at equilibrium. If our equilibrium constant is equal to 1, then neither products or reactants are favored at equilibrium. So overall, this question worked very similarly to the Hess's law question to start with, in that we were identifying our reactants and products in our reaction steps, figuring out if we need those steps to be forwards or backwards so that the reactants and products from the goal equation will be in the reactants or products of the steps respectively. We then need to figure out how many moles of each step we need so that those equations add together to give us our goal equation. Finally, we can calculate our equilibrium constant. Any reaction steps that are forwards, we're going to put the equilibrium constant on the top of the fraction. Any reaction steps that are backwards, we're going to put the equilibrium constant on the bottom of our fraction. And then those equilibrium constants will be to the power of the moles required for those to add up to give us our overall goal reaction.